Section 2, Identifying Minerals. Earth science called mineralogists examine, analyze, and classify minerals. To identify minerals, mineralogists study the properties of the minerals. Some properties are simple to study, while specific equipment may be needed to study other properties. Physical properties of minerals. Each mineral has specific properties that are a result of its chemical composition and crystalline structure. These properties provide useful clues for identifying minerals. Many of these properties can be identified by simply looking at a sample of a mineral. Other properties can be identified through simple tests. Color. One property of a mineral that is easy to observe is its mineral's colors. Some minerals have very distinct colors. For example, sulfur is bright yellow and azurite is deep blue. Color alone, however, is generally not a reliable clue for identifying a mineral sample. Many minerals are similar in color, and very small amounts of certain elements may greatly affect the color of a mineral. For example, corundum is a colorless mineral composed of aluminum and oxygen atoms. However, corundum that has traces of chromium, Cr, forms a red gem called ruby. Sapphire, which is a type of corundum, gets its blue color from traces of cobalt, Co, and titanium, Ti. Figure 1 compares colorless pure quartz with purple amethyst. Amethyst is quartz that has magnesium and iron, which causes the purple color. Color is an unreliable identification clue because weathered surfaces may hide the color of a mineral. For example, the golden color of iron pyrite ranges from dark yellow to black when iron pyrite is weathered. When examining a mineral for color, you should inspect the mineral's freshly exposed surfaces. Streak. A more reliable clue to identify a mineral is the color of the mineral in powdered form, which is called the mineral streak. The easiest way to observe the streak of a mineral is to rub some of the mineral against a piece of unglazed ceramic tile called a streak plate. The streak's color may differ from the color of the solid form of the mineral. Metallic minerals generally have a dark streak. For example, the streak of gold-colored pyrite is black. For most non-metallic minerals, however, the streak is either colorless or a very light shade of the mineral's standard color. Minerals that are harder than the ceramic plate will have no streak. Luster. Light that is reflected from the mineral surface is called luster. A mineral that is said to have a metallic luster is said to have a metallic luster if the mineral reflects light as a polished metal does, as shown in Figure 2. All other minerals have a non-metallic luster. Mineralogists distinguish several types of non-metallic luster. Transparent quartz and other minerals may look like glass and have a glassy luster. Minerals that have an appearance of candle wax may have a waxy luster. Some minerals, such as mica minerals, may have a pearly luster. Diamond, for example, is a mineral that has a brilliant luster. Minerals that lack any shiny appearance has a dull or earthy luster. Cleavage and fracture. The tendency of a mineral to split along specific planes of weakness to form smooth, flat surface is called cleavage. When a mineral has cleavage, as shown in Figure 3, it breaks along a flat surface that generally runs parallel to planes of weakness in the crystal structure. For example, mica minerals, which are sheet silicates, tend to split in parallel sheets. Many minerals, however, do not break along cleavage planes. Instead, they fracture or break unevenly in pieces that have curved or irregular surfaces. Mineralogists describe a fracture according to the appearance of unbroken surface. For example, a rough surface has an uneven or irregular fracture. A broken surface that looks like pieces of broken wood has a splintery or fibrous fracture. Curved surfaces are conchoidal fractures, as shown in Figure 3. Hardness. The hardness of the ability of a mineral, hardness. The measure of the ability of a minerals to resist scratching is called hardness. Hardness does not mean resistance to cleavage or fracture. A diamond, for example, is extremely hard but can be split along cleavage planes more easily than calcite, a softer mineral, can be split. To determine the hardness of an unknown minerals, you can scratch the mineral against these on the Mohs hardness scale, as shown in Figure 1. The scale lists 10 minerals in order of increasing hardness. The softest mineral, talc, has a hardness of 1. The hardest mineral, diamond, has a hardness of 10. The difference between two consecutive minerals is about the same through the scale, except the difference between the two hardest minerals. Diamond 10 is much harder than corundum 9, which is listed on the scale before diamond. The test of unknown minerals for hardness must be determined. You must determine the hardness mineral on a scale that the unknown mineral can scratch. For example, galena can scratch gypsum, but not calcite. Thus, galena has a hardness range between 2 and 3 on the Mohs hardness scale. If neither of the two minerals scratches or the other mineral has the minerals have the same hardness. The strength of the bond between the atoms that make up a mineral's internal structure determines the hardness of the minerals. Both diamond and graphite consist only of carbon atoms. However, diamond has a hardness of 10, while the hardness of graphite is between 1 and 2. A diamond's hardness results from a strong crystalline structure in which each carbon atom is firmly bonded to 4 other carbon atoms. In contrast, the carbon atoms in graphite are arranged in layers that are held together by a much weaker chemical bonds. Crystalline shape. Minerals crystals form in one of 6 basic shapes as shown in Table 2. A certain mineral always has the same general shape because of the atoms that form the mineral's crystals always combine in the same geometric pattern. But the 6 basic shapes can become more complex as a result of environmental conditions such as temperature and pressure during crystal growth. Density. When handling equal-sized specimens of various minerals, you may have noticed that some feel heavier than others. For example, a piece of galena feels heavier than a piece of quartz of the same size. However, a more precise comparison can be made by measuring the density of a sample. Density is the ratio of the mass of a substance to its volume of a substance. The density of a mineral depends on the kinds of atoms that the mineral has and depends on how closely the atoms are packed. Most of the common minerals in the Earth's crust have a density between 2 and 3. However, the density of minerals that contain heavy metals such as lead, uranium, gold, silver range from 7 to 20 grams per cubic centimeter. Thus, the density helps identify heavier minerals more readily than it helps to identify lighter ones. Special properties. All minerals exhibit the properties that were described earlier in this section. However, a few minerals have some additional special properties that can help identify these minerals. Fluorescence and phosphofluorescence. The mineral calcite is usually white in ordinary light, but in ultraviolet light, calcium appears red. This ability to glow under ultraviolet light is called fluorescence. Fluorescent minerals absorb ultraviolet light and then produce visible light of various colors as shown in Figure 4. When subjected to ultraviolet light, some minerals will continue to glow after the ultraviolet light has turned off. This property is called phosphorescence. It is useful in mining of phosphorescent minerals such as eucryptite, which is an ore of lithium. And this word here, I'm going to have someone else say it.
Chatoyancy.
Chatoyancy. Chatoyancy. In reflected light, some minerals display a silky appearance that is called chatoyancy. This effect is also called the cat's eye effect. The word chatoyancy comes from the French word chat, which means cat. and from oil, which means eye. Chatoyancy is the result of closely packed parallel fibers within a mineral. A similar effect called asterism is a phenomenon in which six-sided star shapes appear when the mineral is reflected with light. Double reflection. Light rays bend as they pass through transparent minerals. This bending of the light rays pass from one substance, such as the air, into another, such as the mineral, is called refraction. Crystals of calcite have some other transparent minerals bend light in such a way that they produce a double image of any object viewed through them, as shown in Figure 5. This property is called double refraction. Double refraction takes place because light rays are split into two parts as they enter the crystal. Magnetism. Magnets may attract small particles of some minerals that contain iron. Those minerals are also sometimes magnetic. In general, non-silicate minerals that contain iron, such as magnetite, are more likely to be magnetic than other silicate minerals are. Lodestone is a form of magnetite. Like a bar magnet, some pieces of lodestone have a north pole on one end and a south pole on the other. The needles of the first magnetic compass were made of tiny slivers of lodestone. Radioactivity. Some minerals have a property known as radioactivity. The arrangement of the protons and neutrons in the nuclei of some atoms are unstable. Radioactivity results as unstable nuclei decay over time into stable nuclei by releasing particles and energy. A Geiger counter can be used to detect the released particles and thus to identify minerals that are radioactive. Uranium, U, and radium, Ra, are examples of radioactive elements. Pitchblende is the most common mineral that contains uranium. Other uranium-bearing minerals are carnotite, uraninite, and autunite. That is Unit 2.